Okay, it's 8:30. Let's get started. I hope you had a good break. Welcome back. Think about this thing as a brand new course. Okay. Now, there's a couple of things I want to say, and this is critical for the final exam. Remember, this topic has to do with mechanisms. Okay, and mechanisms is an assembly of things. For example, a single-cylinder engine. It's got a connecting rod, a crank, a piston, a path that it goes up and down. So there's an assembly product file, and there is 4 part files. Okay, all of these have to be uploaded. Okay, and remember, there's 3 problems. If you left each one of them as part 1 for problem 1, part 1 for problem 2, part 1 for problem 3, and you don't pay attention to it, one is going to overwrite the other one, and it's going to be a disaster. There were about 7 or 8 people who did it like that, and everything was in just one gigantic folder and didn't work. Anyway, I'm just letting you know, work on your organization skills so that every problem has its own folder, and try to do 2 problems at the same day so that you see what the issues are. Okay, because if one day you do only one problem and come back the next day do a different problem, you don't see the issue. But if you try to do both problems at the same time, it tells you that you have to be very organized. Otherwise, it's going to be a disaster. But anyway, let's move on. Did I start this? Yeah. Okay. Where is it? No. Oh, record. All right. I was going to do it in bullet form, but it's not working. All right. So I already talked about these things. Next 6 weeks, completely different animal. And later on, I'm going to do chapter 1 today. Everything, including today's lecture, which will be posted, everything is on Teams. Everything. I posted it. Okay. It was also arranged to be posted on YouTube, but you see what happened. So what I'm going to do, it was scheduled to appear 2 days or 3 days before what it was supposed to be, a lecture, for example, 3 days earlier, or a lab 3 days earlier. So I scheduled it like that, but I'm going to go and release it so that everything is public. Okay, so Teams or YouTube, whatever you want. Now, we are switching gears. This is the book. You need it, I don't know, just like whether you needed the FEA book. So unfortunately, these are, I cannot do it in bullet form, so I'll start on the top. You took your you took your machine dynamics course last year with Dr. Magliaro, is that correct? Okay. All right. So notice that the whole idea, I mean, you started with kinematics. Kinematics meaning that, for example, take a single cylinder engine. The crank turns at so many RPM. What you want to know is what is the acceleration of piston, what is the acceleration of the connecting rod, etc. That's kinematic. Just give me the position. I will tell you what the velocities are and what the accelerations are. You just differentiate, as simple as that. Once you do the kinematics, then you move on to kinetics. In other words, okay, now the crank is turning at a certain instance. The connecting rod has such and such, for example, acceleration, or the piston has such and such acceleration that you can find what are the forces acting on it. That's the kinetics part. Okay? Now, I don't know what you did, whether you used software or you did manually. Usually you do manually, and then rarely people do software in that course. Now, once you specify the forces, once you get the forces, and you can do that, once you know the acceleration, you can get the forces. Once you get the forces, then you can do FEA in it, because you have the forces, you have the acceleration, you can do FEA, you can get the stresses in the parts. Okay, so basically what you did with in that course, you assume everything was rigid. Okay, the piston was a rigid body, just a mass going up and down, or a crankshaft or connecting rod, a rigid body which was not only moving but it also translating. Piston only goes up and down, but connecting rod not only moves, but it also translates. Anyway, so let's move on. This is the beginning of mechanical engineering, maybe 2,000 years ago, something like that. Wheels, wheels or mechanisms. And we assume in that course and in this course, we're assuming that everything is rigid. They don't change shape. Bodies are, see, when you look at, for example, single-cylinder engine, it's made of several bodies, okay? It's a mechanism, right? It's made of several bodies, piston, connecting rod, crankshaft, etc. Rigid object. These are connected together at joints, okay? And joints are also called kinematic pairs, okay? It's also called kinematic pairs, okay? Because it takes two things, connect them together. Connecting rod, crankshaft. Connecting rod, piston. So those are joints or kinematic pairs. So you can see a mechanism is made of bodies plus joints. And there are also some mechanisms which are flexible, such as belts, for example, or a chain, for example. Those are mechanisms, but also they change shape, not as an individual piece to develop stresses in it, but the shape is flexible. It changes shape. Now, the purpose of a mechanism is to transfer motion and force. That's really the purpose of a mechanism. For example, a wheel turns because it linearly moves the stuff. Okay, so that's what a mechanism is, the function of a mechanism. Finally, there is towards the bottom, this next 4 or 5 weeks, three of which I'm here. I'm not here. Well, I mean, 2 of each. 2 weeks I'm not here, but the lectures are posted, labs are running, etc. It's going to be looking at many different joints, okay? And the joints, there are different ways of classifying them. One of them is if a joint, such as a connecting rod and a crankshaft, for example, at one point, they're connected to each other, pinned together, okay? Those are called higher order joints, okay? But if two things slide on each other as surfaces, as long as there's surfaces involved, it's called lower order joints, okay? Lower order, higher order. Perfect question for multiple choice. I'm just giving you an example. All right, so let's move on. Are there any questions, first of all, before we do our first problem? All right. First of all, remember, in the machine dynamics course and in this course, we are dealing with objects that move in space, connecting rod, piston, crankshaft, etc. And each object is rigid, like you see on the left-hand side, and the center of mass of that object has 6 degrees of freedom, 3 translations and 3 rotations. So if you take this mouse, for example, going like that, the center of mass, because we're assuming it's rigid, we just put everything at the center of mass, can translate and can rotate, 6 degrees of freedom. However, when you look at, for example, the case of a block on a surface that's sitting there, this block, if it doesn't come off that plane, it's got only 3 degrees of freedom. Translation in the plane and rotation about the normal to the plane. So once you restrain the motion, the number of degrees of freedom is reduced. That top one is called planar joint. Like here, this object on the ground is a planar joint at the bottom, okay? Because it can translate and it can rotate. On the other hand, if I take that same problem and restrict it further, I say the edge of that block moves on the edge of that plate, or along the line. It doesn't have to be edge of a plate, just a line. The edge of that block moves along a line. Then it can only translate one way, 1 degree of freedom. Okay? So that's what the story is. And we're going to look at other joints later on. So far, you saw 2 joints. It's obvious. So the first problem that we're going to do is a block that is translating like that on a track. So it is a prismatic joint. And first I make a cartoon. And cartoons are important because you want to show it to people. How does this mechanism work? They are important, very important. Everything that you see, all these commercials that you see on TV, animation, those are cartoons. There's no physics in there. Okay, so first we're going to make a cartoon. And then we come back and put some physics into it. And the physics that I'm going to put in this problem is that this block not only moves down that track, but it moves at a constant acceleration. For example, 2 inches per second squared. Now, as soon as I say the acceleration of this block is 2 inches per second squared, calculus, dynamics, whatever, statics, you know what the velocity is. Integrate 2, you get 2t. The velocity of that block is 2 times t. T is time. Integrate it again, you get t squared. The position of the block along that path is t squared. You give me time, I'll tell you where it is. We're going to do that later. First, I'll show you the basics of doing these things, and then we're going to do put the physics into it. And how do I verify my physics? Well, I just told you. I just told you that for a constant acceleration, velocity is 2t. It should be a straight line. If I plot this thing, this is not done in CATIA, okay, just Excel or whatever you want. 2t and t squared. Let CATIA generate it and see whether you're doing the right physics or not. Because watching the block move is not going to show you the physics. It's just like a cartoon again. Except that when the block moves with the physics put into it, you see that block starts slowly and then it builds up velocity. If you looked at it, you can see that there's an acceleration. It's more than just a cartoon. Okay? All right, good. Any questions? All right, so let's go ahead. CATIA. I'm hoping this is recording. I think it is. All right. I start in assembly. Okay? Assembly design, double gear right there. Immediately save. So file, save management, save as, desktop, new folder, June 28, first class. How about that? Good. Just a couple of comments about this naming business. Well, I'll get to that in a second. So insert new part in there. And I'm going to call this thing track. Right click, properties, track. This is the instance name, yours, and track. Okay. All it is a box. That's it. So go to part design and make it. So on this vertical plane, I will sketch. Just for the heck of it, I'll make it 1 inch wide. It doesn't have to be. The dimensions of this has nothing to do with the problem. These dimensions have nothing to do with the answer. The t, 2t, etc., or 2t, t squared have nothing to do with the size of these things. Okay. So let me draw something here for you. For example, I will put a dimension. It's a good idea to have an idea of how big these things are for your own benefit. That's all. There, I'll make this thing to 1 inch. Exit. Pad it. Now I'm going to make that thing 20 inches long. Okay, because these things that I showed you a few minutes ago, the formula that I showed you, when t is 20, the distance, when the distance is 20, when you put t squared equal to 20 and solve for t, you get 4.47 seconds. Okay, so after 4.4 seconds, when I put the physics into the problem, this block reaches the end. Okay, you can make it anything you want. Or I'll make it 20 inches. Okay, because I want to show you that there's physics involved later on. After 4.47 seconds, when I put the physics in there, the block is at the end of the track. It can keep going on. It doesn't matter. All right, so this is it. Save everything. On the midterm, I noticed that a few people had done things okay. Then probably they said that, oh, this stuff that I'm doing, these are people who actually mix everything together. They said that, oh, this problem is this part that I made is for problem 1. So they made a right-click rename, added problem 1 at the end, the Microsoft way. Done. I won't be able to read it. Katia will lose track. You cannot do it like that. You cannot just rename something using Microsoft right-click rename. Anyway, let's not worry about it. Then I'm going to insert the block. So insert, new part, in there, I'm going to call it the block. Always say no. Please read this thing once at least so that you're satisfied with why you're saying no. Block. This is your block. And block. And make it. Okay, on purpose. I'm not going to put it in the place where it's supposed to be. I'll do it somewhere on the side. So on this plane, I will sketch, again, a rectangle. The only thing that I'm going to do is make sure that one of these dimensions is 1, okay? Because I want to put it on that track so that it looks nice and tight. 1. Okay, good. Exit. Start right here. And I made this thing 1, by the way. Look, I made this thing 1. Maybe it was better if I made this thing 1 less step, but that's okay, no problem. Because you're going to do a lot of assembly constraints in the next 6 weeks, okay? So I might as well learn how to do that. Okay, good. Save everything. So you can guess a problem like that on the final exam. You did this. How many marks it has? Maybe out of 25, 1. Just to encourage you, okay? Good. Now, when it comes to creating mechanism, you need bodies. We created the bodies, 2 bodies here. And you need joints. The joints can be done manually, or some joints, you can put assembly constraints on it, because this has to be on that track. And the edge must be coincident with the edge, okay? You put assembly constraints on it, and then when you go to the digital markup DMU kinematics, there's a magic wand there. Magic wand is going to try to convert some of those constraints into joints. You have 2 choices. Do it manually, and I'll do that. I'll show you how to do it later on. Or put the assembly constraints and use the magic wand later on. Magic wand will create a prismatic joint if you have the proper assembly constraint. Not all the joints can be done with the magic wand. Magic wand. Okay, let's put assembly constraint. A lot of people ignored this on the assembly problem, which is okay because I told you only if it doesn't run that I want to give you some part marks. I'm going to see whether you have put any assembly constraints or not, okay? Here you have no choice. The assembly constraint must be done and must be correct. Otherwise, you get joints that you will have to delete. You will have joints that you will have to delete and then do it manually or some other way. Okay, so let's see now. First thing that we're going to do, we're going to anchor something that's going to stay put. You already know that, okay? That makes our job easier. And if you don't do that now, later on when you try to animate, it's going to say there is no fixed part, okay? Let me put it this way. Mechanisms are useful only if something is fixed. Imagine 4 bars linked together at the corners. Imagine. And this is floating in space. What good is that going to do you? As soon as you put a force on it, it starts taking off. But if you fix one of the parts, maybe attached it, welded it to the body of a, I don't know, satellite or the rocket, then you put a force, this is not going to fly away. It's going to move. Okay, so we need a fixed part for an assembly, for a mechanism. Otherwise, it's a totally useless thing. So I just fixed that, okay? Now, I want to place this on top of that. For example, I say coincidence between this face and that face, and say okay, and update, okay? And you see they're at the same level. You see they're at the same level. I want to put, for example, this edge on that edge. Now, if I try to do that, they say I can't do it because you're telling me these are at the same level. I may not be able. Let's try it. Coincidence between this and that, and update. You see, so I can't do it. You're telling me these surfaces have to be flush, and then you're telling me the bottom edge has to be on the top edge. So do it any way you want. If I delete that first constraint, if I deleted that first constraint, then it will do it for me. Right there. Do this thing any way you want. The only thing is that I don't want it to be here. I want it to start there. So, for example, you say coincidence between this edge and that edge. Good. Now, if you use the magic wand later on with what I just did, in other words, this edge and that edge being coincident and the back edges being coincident, you will get a rigid joint. Because, hey, says, you're saying that these have to be coincident and these have to be coincident. How can I do that if things don't move? So, you may have to delete some stuff that you don't want. For example, look, this last one, the whole purpose of it was to ring it at the end. That's it. There was no other reason. So I'm going to delete this. I'm going to delete this. But I have this one, the edge and the edge. And I need the face and the face, because that'll give it the prismatic joint. Those two faces stay in contact. Don't look at it as contact. There is a contact there. Don't worry about it right now. Faces stay coincident and edges stay coincident. So this block can only travel down that track. Now, I don't have that. I initially did it and I deleted it because of what I wanted to show you. So I'm going to do that right now. Coincidence between that face. It really doesn't matter. You can make this face and that face. You can make the bottom face and the top face of that. It really doesn't matter. Just to make you happier, I'm going to do right click, hide the bottom of that, the bottom of that. And where's the other guy? I hid it. And the top of this. They stay in contact, coincident. Edges stay coincident. This can only travel. Notice that I could have done the sides also, planar. The sides to be coincident. It would have done the same thing. It'll do the same thing. But I'll leave it like this. Okay, good. Now, how can I check this before I go and create the mechanism? It is possible. Remember the move toolbar? You have done this thing before. You click on it, and there is this checkbox here. It says keep the constraint, keep the constraint, keep the constraint. If I try to translate it in the direction Y, it says I can't do it. I can't do it. If I try to translate it in direction Z, it won't do it. Only direction X will work. That makes sense. Okay, cancel that. Good. Now, this doesn't guarantee that the rest of the problem is going to work, but if you can get things done here, check it out. There's no way it's going to work it there unless you do a lot of extra effort later. Save everything. So notice that two constraints were created, face to face, edge to edge. And the magic wand will automatically convert this thing to a prismatic joint. Now, what do I mean by, first of all, let's save everything. If I move these things apart and update, they may not go back to where they're supposed to. Okay. For example, if I move this thing backward, if I translate it backward, an update, it's going to stay there because face to face, edge to edge is still valid. Just be aware of that. Good. So here's what we do. We go to Start, Digital Mockup, The only toolbar that we use in this course is DMU Kinematics. Of these workbenches that you see here, the only workbench that we use is DMU Kinematics. And as soon as you do that, everything changes. On the top, I have this icon that I keep referring to it. It's very easy to find out whether you're in part design or not. Part design is a single gear. Assembly design is a double gear. I don't know what to call this. I mean, it looks something like here. It looks something like that. I don't know what to call it. So many years ago, I decided to call that thing the pointy hat, witch's hat. Goes like that. That's the only thing that I can think of. I don't know why they put something like that, but right there. Now, this is extremely important. This thing where you have an anchor is extremely important because remember, I told you if you don't anchor anything later on in the assembly design, it's going to come back say, hey, nothing is fixed. You can fix it here, but that's the purpose of that anchor. If you didn't do it there, you can still do it here. I mean, obviously, you can go back and fix it. Right next to it, it's kind of hard to see for you. It looks like two gears and looks something that looks like a pencil to me. But if you look at it closely, it's a wand, magic wand. So you take assembly constraints right up there, and magically, if possible, try to convert it to joints. If you click on it, the first thing is going to say, hey, you don't have a mechanism. You want to create a mechanism? The answer is yes, new mechanism. And then it says, oh, the name of your mechanism, mechanism 1. Would you like to keep it like that? That's up to you. I'll keep it like that. It could be that you want to distinguish between these things. For example, if you're doing an aircraft, the rudder has its own mechanism. The flaps have their own mechanism. So you may want to give them meaningful names, okay? Not mechanism 1, mechanism. Landing gear has its own mechanism, okay? But here there's only a single thing. Just leave it the way it is. Baby stuff. And then on the right side down here, it says auto create. In other words, it detected some joints, that possibility of some joints. Would you like me to magically create them for you? The answer is yes, auto create. Now this went from 1 to 1 to 0 to 1. Don't pay too much attention to it. You say, okay, notice at the bottom of the tree, you got something called application. And you expand it. A mechanism was created. You expand it. The degree of freedom is 1. We already know a prismatic joint has a single degree of freedom. It can only translate in one direction. 1 degree of freedom. Okay? That's why it's 1. It created a joint, and it's a prismatic joint. Okay. Now, when the degree of freedom is anything but 0, okay, anything but 0, you cannot play with it. Because degree of freedom being 1 means that you're in charge. You tell the block where it has to go. You're in charge. 1 degree of freedom. Okay? So if you double click on this, if you double click on that, this dialog box opens up. Notice that this prismatic joint is made of those 2 constraints that I put in the assembly design, right there. And it's going to be length driven. Length driven means that, I mean, obviously, how do you say where the block is? You have to say how far it went, okay? On the other hand, if you have a propeller, that's not length driven, it's angle driven. You will do that later on Thursday. We probably won't see you on Thursday, many of you. Oh, actually, I don't have a class with you on Thursday. Dr. Stoilov is taking my class, but everything is going to be posted. The lecture is posted. Now, if I say length driven, notice what happens. First of all, if you look closely, you see that there is a blue arrow here. This shows you the direction of the motion. If you click on this arrow, it goes the other way around. It goes the other way. But I want it to go like that. No problem. I'm not going to flip it. There's a blue arrow here. You click it, and it goes this way. Now, the other thing is that by default, it gave you a range of 100 inches this way, minus 100 inches that way. That's what it gave. Minus 100 to 1. I'm not interested in that. I want to go between 0 and 20. That's my domain of interest, okay? 0 to 20 inches. So I'm going to change these. I'm going to change this 0 to 20. Not that there's anything wrong with 100 minus 100, but if I do it like that and try to make a cartoon out of it, you see that this guy leaves the track and goes 100 inches that way, and he may go 100 inches that way. I don't want to do that. I want to go between 0 and 20. Now, I say, okay, this is your best friend. You know what your worst enemy was there? You know that in the FEA? This is your best friend. Means that, okay, if you're lucky and you did everything wrong, the mechanism can be simulated. That doesn't mean everything is going to work, because if you had done a rigid joint, it'll give you this, but it doesn't go anywhere. Just be aware. If you don't get this, you have a problem. If you get this, doesn't mean it's going to work. It doesn't mean it's going to work. But anyway, best friend. Okay. So, by the way, notice that in the tree, I got a command because you said it's a length-driven joint. As soon as you check that, this guy appeared. So it is a length-driven joint. You're in charge. That's you, basically. This toolbar that is extremely important, I told you there is an anchor here and there's a magic wand here. At the very end, you see two icons. If you expand that, you see two icons. The first one is basically for you to check yourself manually by dragging this block back and forth if you want. And the one next to it, when you put physics into the problem, not just cartoon, physics, because if you look at it, it says simulation with laws of physics. Okay. Right now we're not doing that. We're just doing just moving around. Click on the simulation with command. Because this is a single degree of freedom, there's only one sliding bar. If it was 3 degrees of freedom, for example, and you made one of them length-driven, the other one angled, you'll get 3 sliding bars. Okay, but here there's only a single degree of freedom. Notice that I changed the range. It goes between 0 and 20. If you drag this thing, I set this thing on immediate, but if you drag this thing, you can play with it. That's a good sign. If this was rigidly attached, you drag this thing, it won't go anywhere. But this is fine. Now, I always rewind. That's up to you. Don't do it. If you run into a problem, fix it. I always set it back where it was. Good. Now, if you want to make a cartoon out of that, this is not going to be helpful because you have to drag it back and forth. There is a tool, there is an icon right here. It looks like 2 gears. It's a simulation. This was simulation with command. You are in charge. This is simulation. You click on this. It says, okay, you've got a mechanism 1. You may have multiple mechanisms here. Which one do you want to make a cartoon of? Something like that. Well, there's only one here. So I select this. You have to select it. And you say, okay. And you see that 2 things open up. This, initially, don't fool around with these, please. Drag it all the way to the end. Insert. Right here, you go to this. When you drag it all the way to the end without fooling around right now, insert. Anything but 1. This 1 means that I want to see a cartoon at the beginning and at the end. Basically, it just jumps there. But if I wanted to go slowly there, a cartoon that goes, this controls the speed, not physical speed, at least visual speed. Okay. So for anything but 1, and then you play it. Rewind first of all. Let me rewind it for you. Play. It's too fast. Let me do it a different number. I don't know, maybe this one. Rewind. I like that. Cartoon. Now, if you want it reaches the end, cartoon has nothing to do with 20 inches, has nothing to 4.47 seconds. That has nothing to do with that. If you want to play it like a ping pong ball, use this. It's called the loop mode. Play it. It goes like this. Okay, no problem. If you wanted to go back and then jumps at the beginning, the 2 arrows chase each other. Yeah, okay. Rewind. Always rewind. Notice that what it did, it created a simulation for you. It created a simulation 1. Now, if you want to create a video file of this so that you can put it in your PowerPoint presentation or something, you have to compile this. You need to create a simulation, and we just did, and then we have to compile it. So right here, where you created the simulation, expand this thing, the second one says compile. Compile. You need this for video and other things. You click on it, it says, okay, would you like to generate a replay or generate an animation file? Let me do an animation file. There's only one code, one format it has, but it works. So it works with everything that I know of. And then do not use one, because if you use one, it's going to jump. There, that's it. That's going to be the video. So use anything but one. So I use, for example, whatever, 0.04. And then you can give it a name. You can put it somewhere, file name. Let's put it in that directory. Here is June 28, 1. That's you guys. So I'll call it my first video. My first video. You put it there. You just wait. Oh, I say okay. Just wait. Takes it to the end. It stops. Let's go and check our folder. We go to our folder. June 28th. My first video. And this is, it's an AVI file. You can put it anywhere you want. Very good. Kill this. I don't need it. It's over there. Now, let's go back to a thing here. Good. So notice that when you do this, I got a video file, but there was no replay here. Okay. Let me create a replay, and again, compile it again. Generate a replay, because if I want to do other things aside from just making a video, I need a replay. And when you uncheck the replay, it's not going to do it for you. So I said replay, and again, anything but one, and it doesn't ask you for a place, because it puts it in the file, in the tree right there. You say okay. Good. Notice that it created replay. You know what we do, lazy people? When it comes to marking your test, I go to the replay. One of the things that I do, I'll check it. Otherwise, I have to go and drag this thing myself or create a simulation if you haven't done it. But that's not the only reason. Because if you want, for example, to know on what path does this point go? I think last year I said you don't have to be a brain surgeon to say that, or an engineer to say that. That point goes on a straight line. But in a complicated situation, connecting rod that is moving in space and rotating a point on it, what is the path that it takes? It's not obvious. You have to create it. Here it's obvious, but the process is the same. So I want to create the trace of that point. And this is why I compiled it, because without doing the compile, you cannot do the trace. Look at this toolbar where we compile. Remember, a simulation compile. Right here, on the very right-hand side, it shows you an icon with a magnifying glass and footsteps or trace. Click on it. It says, okay, what is the thing? What is the point that you want to know where it goes? Well, it says element to trace out. It's that corner point, for example. That corner point. What is the reference product? Reference product is just the ground. It already took it for me. And it does it at 26 points. I don't know. I used to be able to change this thing. I can't do it. Now, what it does, it creates a part for you. See, it says new part. See that? New part. It creates a part for you that you have to save. And if you want, you can bring it in. So first of all, let me go ahead and say, do it. There we are. But this is not safe. On the final exam, I'll ask you to create trace of something. Make sure you save it, because otherwise I don't know whether you have done it or not. Okay, so I'm going to do that with file save management. File save management. Notice that everything is saved except trace. Save as. I'll say my first trace. my first trace. Give it a name that you can recognize. It could be that there's several of them. My first trace. This is all a cartoon, no physics. Say okay. And say okay. And you will see that in that folder, I also have my first trace right there. So I can bring it into the animation file, into this animation. So let me close this. Let me close that. Insert existing component in there, right? In there. It says, which one is it that you want to put in there? This is not the right folder. June 27 is not you. So you go up, June 28. This is the one that I saved, my first trace, and say, good. And I save everything. And in fact, as I said, you don't have to be a brain surgeon to know that. If you replayed this, what's going to happen? No problem. Any questions? We have about 10 minutes to put physics into this. Okay. So close. Okay, good. I don't need this trace. I'm going to hide it. I mean, if it's bothering you, I'm going to hide it. Although it's a part. I'll just leave it to you. No problem. Now, there is a toolbar that you're going to be working for the rest of the semester. It's called knowledge. This thing is usually down here. It's one of the utility toolbars. And there's no way to miss it. There's something called f of x. Function, laws, physics, f of x, right? You click on it. It gives you all the garbage that you have in this model. All the part dimensions, all the shapes, all the constraints. I'm not interested in those. All I want is my mechanism. That's all. So if you notice, this is a long list of stuff. If you drew a circle, radius of the circle is going to be this. This is a database that contains all the CAD basically stuff. I'm not interested. All I want is my mechanism. Click on it. Two things. Where you are. You see that? The second line, it says length, command length, where you are, and the time. The mechanism has only the commands that you give it and the time. It has nothing to do with the dimension of these. So I want to say that the position is equal to t squared. Remember? Acceleration was 2, velocity was 2t, position is t squared. Okay, so I want to say this is equal to time squared. So add a formula. It writes the dimension on the top. The equal sign is already there. Don't put an equal sign. There is an equal sign here. Right there. You see that? Right there. And t squared. Time squared. Now, time is not called t, is not called time. You can rename these things, but I'll just leave it the way it is. Notice that in this column, you have time here, right there. Click on it. That is the weird name for time. Mechanism 1 / twin time. That's what it is. So if you want to type this thing up there, instead of me typing it, just put the cursor here, left click twice. It puts it for you up here, right up there, right up there. Now, to the power 2, star 2, time squared. It's going to give me an error. Let me do that. It's going to give me an error and see whether we can understand what it says. It said, wait a minute. These dimensions don't match. You're saying that the length in inch equal to t squared in time, second squared. These don't match. Okay? And the reason is obvious. It's actually not time squared. It is 1 inch per second squared. Except remember, these are things that you did in both calculus and dynamics, you have to make sure that these dimensions match. And there are different ways of doing it. First of all, if I want to get there, just double click on it, opens up. I want length to be equal to length. So this is time, and there are different ways of doing it. I'm not suggesting that this is the only way. 1 inch divided by 1 second squared. Left side is inches, right side is second squared times 1 inch divided by 1 second squared. There are other ways of doing it. Watch the videos, you see other ways of doing it. I better not get that message again. If I do, come back and fix it again. No problem. No problem this time. You say, okay. Notice that this thing that I put in there appears in the tree as my physics, as my law, as my formula, right there. That's the stuff. And you can always get there by double clicking on this. You can always get there if you want. Here, look. There, cancel. Okay, good. Now, there's the physics. Let's go run it. How do we run? We're going to go to simulation with laws. It says how many seconds? The default is 10. I don't want to do 10 because 10 is going to go off the track. It's going to be over there. No problem. You can do it if you want. 4.47, remember? At the end, when you put 4.47 in that expression, you're going to get 20 inches. So to change that number here, don't go 10. Go 4.47. Say OK. And then you just play it. You just play it. Here, play means this. Don't forget to save these things. If the system crashes, all the stuff that I've done, all these things are lost. You know that. Now, if you watch this thing, you say, well, wait a minute, I don't know this is right. But just look at this thing. It starts slowly and then builds up speed. This starts slowly, but builds up speed, so accelerates. Now, you might say, I don't believe you. This is a visual error. I'm going to say, no problem. I'll plot for you velocity, and I plot for you the acceleration, and plot the position. I better get the constant acceleration, linear velocity, parabolic position. Okay, good. So rewind. So I want to generate a curve like this to convince you that actually there is physics here. In order to do that, you have to create this thing, which is called speed acceleration. I like to refer to it as speed acceleration sensor. It's not hard to miss. It's a ball rolling down a ramp. That's what it is. A ball going down a hill. That's what it is. Speed acceleration. You click on it. It says, okay, well, what is the point that you want to actually plot something for it? Look, it says reference product. First of all, reference product is the track. What is the point? Well, the point, it really doesn't matter. I can take this one, I can take that corner point. It really doesn't matter because they all have the same, this is a rigid body, they all have the same acceleration, same velocity. And this is it. So I had to select the reference, and I had to select the point. If you might say, well, why do we have to select the reference? Because it could be that you want to plot the velocity of that point with respect to something else that moves. But this is not moving. I mean, so in this problem, I want velocity with respect to ground. That's what it is. And we say, okay. Very good. So I created my sensor there. There we are. You can always change it. You can always add more sensors. Maybe you want the velocity of a different point or acceleration of different. You can add, no problem. But here there's only one. They all have the same. Now, if you go that simulation with laws that we did just a minute ago, there is a checkbox here which says activate sensor. I created a sensor. I want to activate it. You click on it. Notice that the last column, it says no. That's because nothing is, I haven't asked anything yet. So why don't I go and find, for example, X vertex, Y vertex, Z vertex. These are the positions of that corner point. But this is dumb as far as the Y and y and z is concerned, because y and z always stays the same. It's x that's changing. So it's ridiculous to choose everything. I'm just going to choose x. Notice that it turned into yes. Then x linear speed, because y linear speed is 0, z linear speed is 0. So x linear speed, here is x linear speed, turned into yes. And x linear acceleration turned into yes. Now, don't close this. Move this thing out of the way. Play it. It's generating those numbers. Generating those numbers. Move it up. Graphics. Oh my God. Hang in there. Obviously, this is wrong. Oh, Z vertex. Damn. I didn't want the Z vertex here. No problem. Close this. Let's go back here. I want X vertex, right? Not Z vertex. Z vertex is always the same. X linear speed and X linear acceleration. Okay, now I have to rewind and do this thing again. Rewind, but when you do that, the history that you just did is already there. Clear this, clear it, because otherwise you're going to get curve on top of curve. Okay, and then don't close this, just move it down, out of the way, play. I'm going to get a line, a constant, and a parabola. Yeah, 6 weeks to do these. Okay, this is the first day. That's why I wanted, don't let these things pile up. Graphics, hallelujah. The red one is acceleration, x linear acceleration. By the way, you move out, you can see it. You expand this thing, you can see it better if you want. X linear acceleration, red, 2 inches per second squared. Look at the scale, it's 2 inches per second squared. X linear speed, the green one, changed. 2t, t is 4.47, almost 9 inches per second. Yellow one is the position. After 4.47, 20 inches long. Now, I'm going to ask you to do these things and generate specific curves that we want. I don't want everything, because you know what's going to happen? Somebody activate all the sensors, all the things, and then give me something with 50 different graphs on. I don't want that. If I say give me these three, give me these three. If I say give me the acceleration, just give me the red one. And then you have to convince me that you have done it, because once you close this thing, it's not going to be in the tree. Print screen. You know the usual drill. I didn't ask you on the midterm, but I will ask you on the final exam. Paste, file, save as, in that folder. Browse, desktop, and I got a couple of more minutes and we're going to be done. June 28. My plot. I'll call it 1. You see why? Good. It's going to be in that folder. I'm going to pull it up, see whether you did it and you did it right or not. Now, suppose, let me rewind, and clear the history. Don't forget to clear the history. Okay. Now, suppose I want the plot, not versus time, of, for example, velocity versus position. Okay? Velocity versus position. This is not versus time. So what you do is you're going to say to options, customize plot, add, it says what versus what. Say if you have already asked for the information, you can select it and do it. If you have not asked for information, your thing is not yes, it's a no, it's not going to do it for you. But I did. Okay, so I'm going to put x position versus x velocity. Okay, so let's here x velocity, x position, this is x vertex, versus x velocity, linear speed, x linear speed, and say okay, it creates this. You see that? It creates that, and then play it. 1 minute. I'm going to be done. Graph it. Oh, I forgot to close this, right? I forgot to close it. That's why I didn't do anything. Rewind. Clear the history. Okay. Already created this thing. Close and then play it. Because while that window is open, it's not going to do it for you. And then you say graphics. Once it reaches the end, there. Position versus velocity, for example. What is this? Let me see for a second. This is inch per second velocity versus position. Not versus time. Anyway, my point is that I don't like this because I don't know I may have done something wrong here. Oh wait, you know what? Oh, this is speed. I'm sorry. This is a speed. This is speed versus position. Speed versus position. Would that be parabolic? One is t squared. I didn't expect it to be like that. But anyway, save. Okay, print screen. This may be wrong. Okay, save. Paste. I didn't like that last block. File. Save as. Browse. Desktop. June right there. My plot number 2. This is it for today. I know you have a test on Thursday. I know that there are other tests coming up. I know that there will be other things coming up, trip to Toronto, whatever. Don't let it pile up, please. I'll see you in about 3 weeks, weekish, right? On the 17th, 19th, I think I'll meet you on the 19th. Everything is going to be there. I'm going to be in the lab today to entertain people. And this opportunity is going to be on Thursday too, but not as long. And then if you can make it these 2 days, come back after I return. And you're welcome to look at your paper if you want.